Today I wanted to finish up on optics, physical optics or wave optics that we've been talking about, a few small items. We started actually talking last time about, oh, by the way, if there's any questions. You might have questions about the exam. Hold off on that because I put a sample exam on the B-Space. And we'll send out a message about the topics on the exam, the rooms, the review sessions, things like that. Hopefully all the details you need to know. If there's still any questions, we can ask them on Wednesday. But I think Erin should be, if she hasn't already, she'll send out an announcement of all the details. Other than that, questions so far? Okay. So here we're talking about the interesting point that even a single aperture, when it's struck by a plane wave, within itself it has a wavefront, and each point on that wavefront is the source of a Huygens wavelet that travels out in a spherical shape out into the space behind the obstacle. And so at points, even in the shadow, the nominal shadow of the aperture, there is a certain amount of light, and it spreads out and interferes. In fact, it could give a minimum at a certain point. If again, we worry about what is the path difference between one wavelet and another. And if the path difference is half a wavelength, then the waves will come back, I don't know if I should call it out of step, but more out of line is the point. They're stepping at the same rate. The frequency is the same. But what's happening is that they're getting out of line like a column of soldiers that splits. And the question is, when they recombine, are they parallel to each other, or have they moved a half a wavelength further? And so out of line, as it were. It's a better expression than out of step because the frequency is the same. It's just that the path difference is different. The path lengths are different, and there's a path difference. So if this path difference here is a half wavelength, then the light from this point will cancel the light from this point. And so we'll get a minimum over here. And then we do the same thing for every point in the aperture. This point is paired with this point, and if it's a half wavelength difference, which it should be, let's just shift it over. This wave will cancel this one, and the next one will cancel the next one, and so on. So they pretty much all cancel at this point, and you'll get a minimum. And so the pattern will look like, in the main part of it, you'll have a bright thing, but at some point, the brightness is dimmed by the interference of these waves, each successive one, this one with that one, this one with this one, and et cetera, et cetera, et cetera. That one with that one. Because if you look at the path difference between each of these, they'll each be a half wavelength. That's the thinking behind this. And so they'll all cancel and give you a net cancellation over here. And then if you go out in further angle, the path differences become not half wavelength, and so you can get another maximum when the path difference, say, is a whole wavelength. In other words, when n lambda is d sine, or a over 2 sine theta, this will, when you have a whole wavelength, you'll get a maximum. So you can get a sine theta is 2 n lambda. In other words, if you have a certain number of wavelengths, you will get so whole wavelengths path difference. You'll get a maximum and subsequent minima. So you get this pattern that looks. Well, I'll show you some pretty pictures of it. So here, for a second minimum, you can do a similar calculation, dividing the aperture into 4 parts instead of 2 parts, and you get the same sort of thing. And then you can test your knowledge with this checkpoint C if you get the right answers. So the general pattern looks something like this. You'll have your forward peak. You'll get the first minimum. You get another maximum. You get another minimum, another maximum. And it will depend on the wavelength and the size of the slit. Okay? So the point of this next thing is that we had a diffraction grating of many slits. And we calculated that there would be diffraction coming from each slit. And if we had a path difference, again, the spacing between the slits we call d. And if we had n lambda is d sine theta, at an angle theta, you would have a maximum because you'd have the waves coming back in line. But now we're also saying that each of the slits themselves sends out a diffraction pattern, which is spreading out from inside it. And so you have this secondary pattern. Well, we have a secondary maximum of this type in the second order. But from each slit, you have a broad peak of light. So the point is that what you finally see is kind of a product of the effect of the interference between slits and the spreading that comes out from any one slit. This is kind of like the envelope of the whole pattern is due to the slit width. Slit width gives you an overall pattern. And the peaks are coming from the interference from the individual slits. So that's what the purport of this slide is. Here you have a broad peak coming from any one slit. And then here you have the pattern of many slits interfering with each other. And the overall pattern of this would be a uniform pattern multiplied by this single slit pattern. Show it again here, I think. You have here the multiple slits interfering with each other. They would give you sort of uniform peaks separated by this sine theta. So this is the multi-slit. Here is a pattern that comes out of one slit. So the pattern you see overall is a multiplication of this by this. And so you see an overall picture that looks like that. Okay? That's if you didn't get it from the book, which is a little bit, I find it hard to understand until you think about it a while, but that's the overall picture. And here's actually some pictures of it. You see you have many lines coming from the fact that you have a double slit. There's 2 of these, but they interfere many places, and you get these narrow lines. But on the top of it, each individual slit is putting out a broad pattern, very bright in the center, a minimum, and a secondary maximum. So this pattern here by double slit is a product of the sharp interference of the 2 slits with each other times the broad pattern from the one slit. So that's what's going on here, okay? So see, so here it is, the closely spaced bright maxima are the interference from the two slits that are separated from by the distance d. But because the slit A width is relatively small, the pattern from each of them spreads out, and so that's the intensity from the single slit. So here, in fact, is the formula that's in the book. You have two parts. You have the maximum intensity, but the beta part depends on the d. That is the spacing between the slits. That's this part. And you see it's multiplied by something that's related to this thing alpha. This beta has to do with d, and the alpha has to do with the width of the individual slit. So that's why you're getting this product sort of thing. One is the thing we first calculated, namely all those lines due to the interference of 1 lambda path difference, 2 lambda, 3 lambda path differences, you have all those sharp lines. And then the other one is that you have the emission from each individual slit, giving you this factor. And that gives you the overall peak, trough, and within that are the sharp lines of the double slit. In case you were wondering, that's what's going on there. Then the other thing that I wanted to quickly touch on was that the fact that so far we've been dealing with slits, sort of rectangular shaped things. We also get diffraction from other shapes. You can get, for example, a common one is a circular aperture. And again, because you have an edge, and the wavefronts are coming in from here. They pass through the aperture, and they will spread into different places by the Huygens construction. Each point on the wavefront sending out wavelets, and you get some waves going off in this direction and in this direction. And it's perhaps not surprising, it shouldn't be at this point, that at some points you will get a cancellation. And as a very rough estimate, let's say you do something like this. We take the separation between, say, the center of this aperture. Let's call its radius A. And again, it's the same old game. We have an angle at which we're going to see this thing. Deviation by this. This is the angle here. So if you have A times the sine of theta will be the path difference. This will be the path difference. And if that's a half wavelength, it'll give you the first minimum. Now this is a very rough calculation because it isn't a square shape. But anyhow, it's not too bad because we get that sine theta is equal to lambda over 2A. And okay, well the book, he puts it in terms of d, which is the diameter of the slit. So 2A is the diameter, so it's lambda over d. I should have put approximately. So that's not bad. I'm off by 20%. The actual answer is the actual answer is 1.22 lambda over d. So that's not too bad. So it gives you the physical idea that what's happening is that light from the inside here is canceling with light toward the edge and canceling to give you the first minimum of the circular diffraction pattern. The picture's a little bit more complicated than that. Remember, we had this demo where, depending on the size of the aperture, I could get maxima and minima. That's when the size of the aperture is much bigger than the wavelength, and then you get all kinds of complications setting in. But if the hole is small, this is the kind of shape you're going to get. You see that? I mean, it's the same story repeated over and over again. Namely, you have a wave, you break it somehow into two parts, which travel different lengths. You look at the path difference. If the path difference is a whole wavelength, they constructively interfere. If it's a half wavelength, they will constructively interfere, and you have your interference and diffraction patterns. So, yes, Matt? That's a convention notation, but it doesn't have to be. If you like, I could call it R. Would that have been easier? You'd have no. I would never assume. I would always. There is no special notation here. It isn't like c is always the velocity of light. It would be defined in the problem. A good problem should define all its terms, sure. If not, ask, because it might not be what you're conventionally expecting. The other thing that comes out of this is resolvability, and that is if you have a spot like this, and suppose you had another spot over here, at what point can you actually see that there are two spots? Because this guy is going to produce a pattern also. And as I get closer and closer, in fact, let me show you very nicely. I have a demo. If I can find it here. Let's see. Yeah, I think we should. Oh, nice. Can you see that? Yeah. Here's a nice demo where we have, in a sense, two spots. And let me. What's nice about this, I can actually pull them apart. So you can see there are two diffraction patterns coming presumably from two apertures here, and this is producing its major peak and its minor peak, and so on. And what's nice is that this demo from someplace, Florida State somewhere, allows me to bring them together. And you see, the question is, when I bring them together, are they resolvable? So far, yes. I can sort of see up in this pattern here that there are two spots. But if I bring them closer, now, are there still two spots? And you see, this is very nice. It says the Rayleigh criterion has been reached. Namely, now it's not quite resolvable. So in fact, I should pull it away. Let's see what I can unresolve. So here they say, well, I can sort of see that it's 2 because there's a little bit of a notch here. So this is interesting. So here, the Rayleigh pattern, there they say no. Well, it's a little bit in the eye of the beholder, whether you want to call that resolved, and it's fractional, but it's approximately there. Now, what's interesting is that according to this, if I make the wavelength shorter, the angle at which the maximum occurs decreases, so that I can squeeze the width of this first maximum down by making the wavelength shorter. In other words, the angles appended by this can be made less. So in other words, in principle, if I go from red light to blue light, I might be able to resolve them. And according to this, right now it says they're not resolved. There's one splotch here. But if I go from red to blue, even here, it's no longer unresolvable according to the Rayleigh criterion. So by making the wavelength shorter, I can resolve it better. This has very important consequences, because if you're trying to say have a CD, and you're trying to put information on the CD, you put little dots. And you're supposed to be able to read that you have little dots separated by from each other. But you have to be able to resolve the two dots. When it's two dots, you want to see two. You don't want to see one blurry one. So you may have heard that what they use inside your CD player is a laser. And the trick is to get the laser with the highest possible frequency, the shortest wavelength, so that you can put the dots closer together with a short wavelength thing, and you read it with a short wavelength thing so that you can get more dots per inch, so you get more dots on your CD. You heard maybe Blu-ray things? Well, the reason they use Blu-ray rather than red ray is because this is the reason. See, because in blue it's resolved, but if you use red, it's not. See, you violate the Rayleigh criteria. So that's why the pressure is to make shorter and shorter wavelength lasers. In fact, it was a big breakthrough when a Japanese fellow about 15 years ago he got the material in which you can make a solid-state laser in the blue region. And that was a big breakthrough. Everybody grabbed it and started making CDs with the blue lasers. And this is why. I'll show you other applications. Well, a rather pretty one. So here's the issue again. It's how close you can bring two objects, two circular apertures together and still resolve them. And I think that's pretty well demonstrated. So this is the angle. Let me put on the presenter view just for fun. It's prettier. All right. So and here's a fun example. I don't know if you're familiar with the painter George Seurat, who painted what's called pointillism. You're familiar with this, huh? This was about 1900, and the idea of the theory of color was being challenged. And Seurat wanted to use pure colors. But so how do you get mixtures? He said, well, I'm not going to mix my paint on a palette and smear it on the canvas. I'm going to put down pure paint, dots, points. And I'm going to say that if you stand far enough away, your eye will not be able to resolve the dots. And so your eye will mix the color. That was his theory. Your eye will mix the color because I'm standing far away and the 2 points should go together. So that's the theory of pointillism. So if you look really closely above the dog, here, just at the edge, he's got points of dark paint and light paint, and actually it's little splotches here. And the idea is if you stand far enough away, that's going to look like some intermediate color. That's the theory of pointillistic painting. And the reason somebody even wrote a play recently, Sunday Afternoon with George Seurat on the Isle de Conjat. There was a whole play of somebody put together. Anyhow, the point is here that, point again a joke, but the color, suppose the color dots are separated by, say, 2 millimeters, about like that. And the pupil of your eye, now that is acting as this aperture. So the question is, if you had 2 dots of color, here and here, 2 millimeters across, how far away do you have to go for your eye to merge that, for it to look like one dot? That's the physics now. I'm sorry. So you have your 2 dots here, and you have an eye which is what do I say, 1.5 millimeters. So our A, or let's say D. So yeah, let's say D. And we say sine of theta is like 1.2 2 lambda over D, something like that. So the point would be that the angle here is given by this distance, let's say 2 millimeters or even 4 millimeters, let's say 2 millimeters between centers. And the question is how far away do you have to be in order to resolve that such that the angle is greater than this so that you can actually resolve it. And the angle here is this 2 millimeters over this unknown length would have to be 1.22. And the smallest angle would be, let's see, well, we can make it red. We'll put in the wavelength of red, say, and over the aperture of the eye. And that'll tell you how far away you have to be in order for the pointillistic effect to work for you. Something like this. So I did it for blue light, okay. So this is the smallest, all colors are merged. Oh, I see. Red with a larger merges at a smaller angle. So that's the furthest you can be away. Well, that's the least. Oh, I guess it's closer you are with the blue, the red will already have merged. That's right. Okay, that's right. Okay. So that's the general idea. Oh, and the other thing where this comes in is very big in the computer business. The point being that the way computer chips are made, like the chips in your cell phones, computers, what have you, is by shining light through masks. And what they do, they shine light through a mask and onto a photosensitive material. This is called a lithography process. And what it'll do, the light will change the solubility of this plastic material, usually some organic material, such that, for example, it might make it more soluble in some solvent. So then you can wash away the material here, exposing the silicon underneath. And then what you do is you send in beams of, or chemically, or with a chemical means or other, introduce impurities into the silicon, which changes its conductivity. So what you're trying to do is make very small apertures, because you want to pack as many lines and chips on a circuit as possible to get into your cell phone. And they can do incredible things, millions of lines per inch. Well, is that right? Yeah, it must be, because I have millions of circles, millions per square inch anyhow. In fact, so what you want to do in a case like this, you want to use as high a short wavelength as possible. They use ultraviolet. They've gone so far as to using X-rays. IBM has a beam line up here, the synchrotron machine, where they're using X-rays from the synchrotron to expose these various resists, called resist, and so producing very sharp lines or grooves in the protective material so they can introduce the impurities in here. In the synchrotron, for example, the beam is going around at a very high rate, and it radiates. Because it's accelerating, it's going in a circle, it radiates X-rays, and so people have pipes which lead the emission, the radiation on various things, and one of the uses is to expose and to work with and try to learn how to make smaller and smaller circuits. Here's another one.